Hello everybody, welcome back. So today we are going to go through the 2024 paper 2, continue with question 5. Okay, so this is like a database question. Sometimes this kind of question scares off students quite a bit because there's a lot of things to read through, but just keep calm and analyze the question. Okay, write down what you need to and then basically just dissect the question before you start. Okay, so here it says ocean dissolve ions, then they have this analysis, 6 most abundant ion. So here in this table 5.1 you have a list of the 6 most abundant ion. They said calcium and magnesium 2 plus, calcium and magnesium, okay, they have a certain concentration. Can be found, their concentration can be found by titration with EDTA. Okay, EDTA is one kind of a hexadentate that you learn in transition element, which can form complexes. Okay, they also have an indicator X in alkaline solution. Okay, so this is a titration in alkaline solution using indicator X. Okay, so the cation ions, they will present as Y2 plus in this question. When indicator X is added to seawater, right, it forms a complex with one of the cation ions, Y2 plus. And the complex is pink in color and it has this formula. So basically the indicator itself with the cation ion, okay, it is pink in color. If it didn't form a complex, right, if it's just the indicator, it will be blue in color. Alright, so just take note of that. Okay, when alkaline EDTA is added to a solution containing this complex, right, the complex ion EDTA Y2 minus is formed. Okay, so basically it kind of replaces the X, which is the indicator. Okay, it kicks out the indicator. Okay, so this reaction 5.2 actually happens. And X remains, the solution turns blue. Remember X, right? X by itself, it is blue in color. Okay, so when EDTA comes in, it kicks out the indicator, turns back to blue. Okay, so they have these 2 titrations. Let's look at the first one. 1 cm cube, need to take note of this later for the calculation. Of the seawater is added to 50 cm cube of DI water, followed by a few drops of the indicator X. Okay, so the pH is at 10. Okay, 0.00375 mole per dm cube of EDTA is added until a permanent color change appears. Okay, the total volume of EDTA added is recorded as well. Okay, then you have a second titration. This time around, they use 3 cm cube. Okay, instead of 1 cm cube, you have 3 cm cube. Okay, then they add a few drops of X, then NaOH is added until the mixture has a pH of 12. Okay, just now was pH of 10, right? Now it's pH of 12. So under this condition, it is assumed that magnesium has been removed as magnesium hydroxide. Basically, it's a precipitate. And only the calcium ions are available. Okay, and then the same EDTA is added. Total volume added is recorded. Okay, so the first round of titration, you used up 16.8. Okay, this titration, right, actually you use it for both calcium and magnesium. Okay, but the second titration, the magnesium has been removed using the OH minus. So basically this second titration is only for calcium. Okay, the complex is only formed for calcium. Alright, so let's get on to the first question. At pH 10, right, the indicator species may be represented by HIN2-. Complete this equation to show how X behave as an acid. Okay, so to behave as an acid, it needs to donate away this H plus. Okay, so we are also told, right, if you look at the previous equation, here, your X indicator combines with the cation to form the complex. Okay, so this is a complex with indicator plus the cation. Indicator with complex with indicator and cation. Okay, so if you have this equation, the indicator In should combine with calcium. Alright, overall it should give you like so it is H plus and then it's a -1. You should get a calcium. Overall it should be a minus. Okay, and then you get a H plus outside. So on both sides, right, your charges should add up to 0. Okay, so your indicator behaves as an acid. This is actually your X. Okay, so it donates away the H plus, it forms a complex. This here is a complex with the calcium cation, which overall gives you a negative charge. Okay, then they want you to state the color of the water sample with X, which is actually we highlighted previously, right? It was blue if it's by itself, and then once you add in the cation to form the complex, it should become pink in color. Where is it? Pink in color here. So blue to become pink. Okay, so the answer here is blue to pink. Okay, let's look at part B. Use the information in table 5.2. What's 5.2? Okay, this titration values, yeah. To calculate the values of U, which is concentration of magnesium, and V, concentration of calcium. So basically, they want you to solve for U and also V. Okay, so this should be quite straightforward enough. You basically just use the concentration of EDTA because it is 1:1 to your cation. So you just take the concentration multiplied by volume of EDTA used. For titration 1 is 16.8. Okay, so basically for the first titration, right, titration 1, you take to find the amount, the number of moles of EDTA, you're gonna use 0.00375 multiplied by your volume, which is 16.8 over 1000. You get 6.3 times 10 to the power of -5. Okay, so this is the number of moles of EDTA. Take note for titration 1, right, it is used for both magnesium and calcium. Okay, then of course you need to use the same method to do titration 2. Okay, do take note, titration 1, right, is actually for 1 cm cube. Okay, titration 2 is for 3 cm cube. Okay, so basically you have to list out in your statement, let the examiner know that you're aware that you're calculating for different amounts of the seawater. Okay, so titration 2, number of moles of EDTA. This is primarily used for your calcium only. 375 because you use the same EDTA. 8.00 times 1000 equals, what is the value here? 3 times 10 to the power minus 5. Okay, so this is for 3 cm cube of calcium, only calcium. Okay, so if you want to like standardize it, you will divide this value by 3, divide by 3, then you will get 1 times 10 to the power minus 5 moles of EDTA if it was 1 cm cube. Alright, so you just take the total amount of EDTA used for both cations minus off the amount that you use for calcium. Alright, then you will get the amount of EDTA, which is the same as the number of moles of magnesium. You just use it, take the first value, divide by this second value. Alright, then you will solve for number of moles of magnesium. Okay, so this second point is actually the answer for your calcium. Okay, got it? So this is the number of moles of calcium 2 plus in 1 cm cube. Okay, so basically you need to divide by volume, divide by 1 over 1000. Okay, then you will have your answer. Okay, same thing for the magnesium, right? Magnesium. Okay, you just take your answer in 1 minus the answer in 2. You have number of moles of magnesium. You take this number of moles of magnesium, divide by 1 over 1000. Okay, that will give you your answer, which is concentration of magnesium. Okay, so this one here is concentration of calcium. 2 answers worked out. Alright, okay, so that's it for part A and B. Okay guys, welcome back. We are going to continue with question 5 from paper 2 of 2024. Okay, let's look at part C. Ocean 2, now we're dealing with a different ocean. So earlier on we had the first ocean, this is the second ocean. Concentration of one of these ions listed in the table earlier, right, is calculated by adding excess of barium chloride. So looking at this barium chloride, right, you need to understand that most of the time you have to look at the ions individually. So what is the chloride going to test for? Usually it tests for silver, but we don't have silver in the table. Barium usually what is testing for? Testing for sulfate, okay, which is actually present in our table here. Okay, we don't have silver, but we have sulfate. So the precipitate that is formed by adding barium chloride is basically, hold on, this is barium sulfate. Okay, so it's dried to constant mass. They say the mass is 0.658. So the ion is SO4 2 minus. Okay, you can just write that in. Calculate the concentration of Q, okay, the sulfate. Okay, so you just take the mass. Mass is 0.658, divide by the MR. Okay, just take it, divide by the MR. That should give you about 0.002819 moles. Okay, so this is the number of moles of sulfate ions. Okay, since they want concentration, right, you just take this answer, go on and divide by 100 over 1000. Okay, so you should get concentration of sulfate equals to 0.0282. Okay, round off to 368 mole per dm cube. Okay, so that's it for part C. Fairly short question. Let's go on to D. Okay, so A, B, C is basically your titration calculation. D, we are talking about KSP, solubility. Okay, so sample of seawater from ocean 2 contains this 0.005 mole per dm cube of calcium and 0.04 mole per dm cube of magnesium. Okay, so this ocean 2 seems to have a lot of magnesium compared to calcium. The KSP for the metal hydroxides are shown. So very nice, they have shown you the KSP. Use your knowledge of KSP and then the information in this table 5.3 to explain why calcium 2 plus remain in solution at pH 12 but magnesium do not. Calculations are not required. Okay, so a lot of times students, when they come to solubility, right, they will try to do the calculation to prove something, but here they say calculation not required. So basically you have to look at this two value. Okay, so KSP, right, I've told my student most of it is like a capacity for ions. So if you look at magnesium, right, this capacity for ions, capacity to hold ions, right, is very, very low. It's like 10 to the power minus 11. Okay, so at pH 12, you're gonna have the ionic product greater than the KSP of magnesium hydroxide. Okay, so for calcium, right, the ionic product is still lesser than the KSP. Okay, but for magnesium, the ionic product becomes greater than KSP because KSP for magnesium 2 plus is very, very low. Magnesium hydroxide is very, very low. Okay, maybe I shouldn't write just the ion. This is calcium hydroxide. And then this side is magnesium hydroxide. Okay, so because at pH 12, magnesium, you're going to have ionic product greater than your KSP. That's why you will precipitate. You will form a precipitate. Since KSP greater than ionic product for calcium hydroxide, it will remain in solution. Okay, then the last part, they want you to show by relevant calculation that almost all of magnesium in the sample forms a PPT. So what have we got? We have got the KSP expression, right? We can write it out. KSP equals to magnesium 2 plus OH minus square. Okay, so what have we got? At the pH 12 will allow us to calculate concentration of OH minus. So you just sub that value in, right? Which is 10 to the power of minus 2. Okay, sub that in. The KSP value given here, you just substitute into the KSP. Okay, just take away this part here. Just substitute into KSP. Alright, so once it's substituted into the KSP, you can calculate the amount of magnesium left, and if you've done the calculation, right, the amount of magnesium left is 1.1 times 10 to the power minus 7. Okay, so this amount is very, 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 very small compared to the starting, which has 0.048. Okay, so it is a very, 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 very small percentage, almost negligible. Okay, so almost all form the precipitate. Okay, only left with this very, very small concentration of magnesium. Okay, so that is it for part D of question 5.